Okay, last one. We're almost there. We're going to do glycogen. Oh, I'm sorry, gluconeogenesis. So, gluconeogenesis is your way of making glucose because there's parts of you that need glucose, whether you're eating it or not. So, the most common example you're going to hear, of course, is red blood cells. They need glucose because they have no mitochondria. So, they need glucose to be able to do glycolysis to be able to get the energy they need. So, when we did gluconeogenesis, we used this diagram. Probably not the best one for actually learning it, but I used it for teaching because it has glycolysis and gluconeogenesis side by side. So I've got glycolysis coming down the page on this side, gluconeogenesis coming up the page on this side. The reason it's so useful to have them side by side like that is this. The reversible reactions just reverse. Because remember what regulates a reversible reaction. Delta G equals 0, so it's all equilibrium based. If I make a whole bunch of what was the product going one direction, that'll make me turn around and make more of the reactant. So delta G equals 0, I go whichever direction, I need to go to reestablish an equilibrium. So you already knew those. So you went into this knowing 70% of it. That's why it was so nice to have this diagram when we did it in class. How often do you start a topic already knowing 70% of it? So then all we had to do is look at the irreversible reactions. So the glucose to glucose 6-phosphate reaction of glycolysis, fructose 6 to fructose 1,6, and phosphoenol pyruvate to pyruvate. Those were the ones that we had to bypass. So bypass is the term you're going to see when we're talking about gluconeogenesis. So going the glycolysis direction, hexokinase converted glucose to glucose 6-phosphate. I got the phosphate from an ATP. ATP went to ADP. Of course, I got the energy too. I put the phosphate on carbon 6 to make glucose 6-phosphate. So to turn that reaction around, I replace hexokinase with glucose 6-phosphatase. It takes the phosphate back off of glucose 6-phosphate. Easy. Gives me glucose back. Easy. But it does not give me ATP back. I don't have the energy to do that. I take the phosphate off and I just leave it there. So when we talk about reversing the reaction, we're reversing what's going on with the glucoses, the glucose and the glucose 6-phosphate. We're not reversing what's going on with the ATP. So don't let anyone trip you up there. I don't make any ATP in gluconeogenesis. Gluconeogenesis costs me energy. Energy-wise, it's not a good deal for the cell. Then, with the reaction of fructose 6 going to fructose 1,6 in glycolysis, where I used an ATP, phosphofructokinase catalyzed it, put the phosphate this time on carbon 1, so I have fructose 1,6, phosphates on 2 carbons, as in the bis, 1,6 bisphosphate. To turn that around or to bypass it, I replace the phosphofructokinase with fructose 1,6 bisphosphatase. Easy. Takes the phosphate off of carbon 1, leaves me with fructose 6-phosphate. However, does not give me an ATP back. So again, I'm reversing what's going on with the fructose. I'm not reversing what's going on with the ATP. I'm just getting a phosphate, leaving it hanging out again. So again, keep in mind, gluconeogenesis is not a good deal in terms of energy. So that's those two bypasses done. Then my last reaction of glycolysis took phosphoenol pyruvate to pyruvate. I made an ATP doing it, and of course the downside of this diagram, don't forget all these little 2's. And that's why I discouraged you from using this diagram to study from. If I were you, And learning this or studying this or going back to this, that's the important part after being away from it for a while. Doesn't matter if you start at the top of the page or the bottom. Take two pyruvates, go through all your steps, put them together, and get a glucose. Even though these two sides are absolutely identical, just having them in your face is good to keep you from forgetting them. These twos are just way too easy to overlook. So I took two phosphoenolpyruvates, went to two pyruvates, made two ATP and pyruvate kinase, did it. Now, if I want to turn this around, take pyruvate back to phosphoenolpyruvate, I do it in a two-step process. So this is one of the reasons I said don't number your steps. I'll hear you guys saying the regulatory steps are number or whatever. It just depends on how you number them. This pyruvate to phosphoenolpyruvate, some books will call one step, two parts. Some books will call two steps. Doesn't matter, just as long as you know what you're doing. So pyruvate goes to oxaloacetate, cost me 2 ATP doing it. Oxaloacetate then goes to phosphoenolpyruvate, costing me 2 GTP doing it. So I'm using 2 ATP and I'm using 2 GTP. All right, well, that's okay. We said it's an energetically expensive process, but two steps or two reactions is two enzymes. I've got pyruvate carboxylase and phosphoenolpyruvate carboxykinase replacing pyruvate kinase. Oh, great. As you know, questions are often answered contrasting glycolysis and gluconeogenesis. And the questions will be something like, all the following enzymes belong to one process except. So they're all glycolysis enzymes except one gluconeogenic, or vice versa. Find it, pick it. And of course, these, sounding so similar, are very likely where your except is going to come from. Because they're all pyruvate, phosphoenolpyruvate, carboxylase, carboxykinase, kinase, whatever. So I would make sure I was really solid on these enzymes. So that's a good thing to know. Another thing that's a good thing to know is how many ATP does it cost me to make a molecule of glucose by gluconeogenesis? We're going to have a plan A and a plan B here. So actually, I'm going to erase all this just to have room. Okay, so to go from pyruvate to oxaloacetate, I'm going to use 2 ATP. To go from oxaloacetate to phosphoenolpyruvate, 2 GTP. Don't forget, we've got the phosphoglycerate kinase reaction here. Here's the problem with that reaction. We make a big deal about that reaction in glycolysis because its significance in life in glycolysis is that it's the first reaction of glycolysis in which you form ATP. Old classic traditional question. In gluconeogenesis, it's no big deal, just one more, who cares, reversible reaction. So we talk about the enzyme a lot in glycolysis. We don't talk about it typically in gluconeogenesis, but it's an enzyme of both because it's a reversible reaction. So it goes with both processes. Don't forget that. Don't assign it to glycolysis and forget that it's a gluconeogenic enzyme too. But anyway, 2 more ATP there. Then we have these 2 NADHs that we lose when we turn that reaction around. So the how many ATP question, I'd have a plan A and a plan B. So plan A, for how many ATP does it take? Takes 2, 4. So if 4 is offered, I'm going to take 4, pick 4 ATP to make a molecule of glucose by gluconeogenesis. If 4 is not offered, I'm going to count these 2 GTP as 2 more ATP. I'm going to count these 2 NADHs is 6 more ATP, not accounting for heat. So plan B is 12 ATP as my cost for making a molecule of glucose by gluconeogenesis. The logic there is this. It's kind of like you have a check that a patient paid a copay with a check. It's sitting on your desk and you spilled your coffee on it and lost it. And I know in reality you can get another check, but go with it. So I never had the money with that check, but since I lost the check, damaged the check, whatever, now I'm not ever going to have the money. So it cost me that money. I use these two NADHs. I use these two GTP. So in effect, it costs me those ATP because I'm not going to get them now where I use the other molecules. So plan A 4, plan B 12. Then the last thing on gluconeogenesis, and this is always the toughest one. If I'm in the cytoplasm, this is your malate story. I go from pyruvate in the cytoplasm to oxaloacetate in the cytoplasm to phosphoenol pyruvate in the cytoplasm, so on back to glucose. No problem. That's exactly the way we always tell the story. However, if I'm in the mitochondria with my pyruvate, I have an extra step, and this is the same thing with the shuttle. I make and unmake something, and if you see a reaction where you see something being made and unmade, the reaction forward then backwards, and you're looking at it thinking, well, what was the point of that? I just went in a circle. I accomplished nothing. The point of it was very likely crossing a membrane, or I dropped off part of a molecule and put it back on. The point was very likely crossing a membrane. So anytime you see a do and an undo, and you're looking at it thinking, well, why? That is probably your why. So I start with my pyruvate. Let's say the pyruvate's in the mitochondria. I still go to oxaloacetate in the mitochondria. Now, instead of going to phosphoenol pyruvate, I'm going to malate in the mitochondria. Now, my malate will cross to the cytoplasm. Back to oxaloacetate, phosphoenol pyruvate, glucose, whole story. Okay, so here's the thing, and this is what messes you guys up. You guys have no doubt about malate being made. You guys love you some malate. Malate's your favorite molecule. If I ask you anything about gluconeogenesis, you are just dying to pick malate. Think of your favorite candy. Not Reese's. So let's say your favorite candy is M&M's. You can't have one M. It just doesn't do it. An M. What's an M? You need M&M's. So here's what your M's are. You only get malate if you're in the mitochondria. So no mitochondria, then no malate. If I'm in the cytoplasm, my pyruvate's in the cytoplasm, I don't need malate for anything. I'm in the part of the cell I need to be in. So statistically, the two worst performing questions ever are the reason for being for the shuttles and electron transport, the whole NADH thing, where'd I make it? I made it in glycolysis in the cytoplasm, and the M&Ms, the malate. You guys, if you see malate in front of you, just want to pick it. Don't pick it. It will be right in front of you. It will be right in your face. Don't pick it unless you're in the mitochondria. So can't have one M&Ms, no malate unless you're in the mitochondria. And that's it for gluconeogenesis.